So today we're going to do a limit of a sum, which are oftentimes really nice problems relating to Riemann sums. So in this kind of form, you might also recognize a Riemann form popping up. Now, if you don't know what that is, don't worry, I'll explain it later. It's basically the limit definition of an integral. So we'll definitely get into that. That's a major hint to solve this problem. So maybe let's get into the solution and see how we can use some beautiful Riemann sums. So we're going to get the limit as n goes to infinity of the sum from k equals 0 up to n, and then sum of n over n squared of k squared divided by n squared plus 1. And so all we've done there is we've just taken this n squared out. So we can redistribute that to get the same sum again. But let's see why we've done that. So maybe we can take this n and this n squared and we can put it in front because it's not depending on k. So we're going to get the limit as n goes to infinity of 1 over n times the sum from k equals 0 up to n of 1 over k over n squared plus 1. So this is the next step, and now we can actually already use some Riemann sums. Now this is probably the hardest part if you're doing this on your own. Recognize that you can use this Riemann sum here, but let's see why it's so useful in this case. So let's start off by defining a Riemann sum. Let's say we've got this definite integral from a to b of a function f of x dx. Well, we can define that as a limit. So of course the integral is defined as an area under a curve, and we can also define a limit by some kind of infinite approximation, which is going to be a limit. So basically we're going to get the limit when n approaches infinity of b minus a over n times the sum from k equals 0 up to n of the function we're integrating over, so the function f of a plus b minus a times k divided by n, all in this function. So if you've never seen this kind of formula, I bet it comes out of the blue like it makes no sense at all, but actually it's quite a logical formula. So I'll explain it quickly using some visual tools, and then we'll move on. If you have seen this before, you don't actually need to worry about it. You can skip this next part, although it's quite a nice argument. So let's see how we can intuitively understand a Riemann sum by looking at some graphs. First of all, we've got this function f of x, which is going to be minus x times x minus 2. Of course, this could be any function we're going to generalize along the way. But let's say we've got this function to make things a little simpler. Well, we can take an integral from 0 to 2, and this is not a difficult integral. We could solve that immediately, but let's see how we could approximate it maybe by using some rectangles. So let's say I use a bunch of rectangles, like 6 in this case, and I guess this would be a fairly good approximation of what the actual integral would be. But maybe let's see how we can calculate each of these rectangles areas. So first of all, the length is going to be b minus a over n, n being the number of parts we divide this interval up into. So let's see, b minus a, that's going to be the total length. So in this case, that would be 2. So b minus a, that would be 2 minus 0 for integral there. So that would be an integral from from a to b, and we just calculate the total length by b minus a. Then we divide up into a number of parts n, and each length, each base of these rectangles is going to be the exact same length, b minus a over n. So I hope that's clear. Now secondly, we should look at exactly the height of each of these rectangles. Now the height is going to be given by our function, right? So we're going to have a function which we can evaluate at x of k. And what do I mean by x of k? It's just going to be the kth part of our interval. So let's see how maybe we can write that. So k is going to go from 0 to n, because there's going to be n parts in total, or actually in that case n plus 1, but that doesn't really matter. Let's say k is equal to 0. Well, then we start at f of a, which is going to be the beginning of our interval. So that's logical, right? Now let's say if k is equal to n, so that's going to be the end of our interval. Well, that's going to be a plus b minus a times n over n, which is going to be b. So then we're going to get f of b. So in general, what this k is going to do is, as it goes along, 0, 1, 2, 3, and so on up to n, it's going to take each part of our function evaluated at x of k. So just add a little bit of the total length b minus a each time. So that's a pretty intuitive explanation of the height of our rectangle at each step as well. Now you should maybe ponder for a little while if you understand what's going on here with this part of the function. Now of course we want to find the areas of these rectangles. So that's going to look like this, right? Now the area of a rectangle isn't difficult, it's just going to be base times height. So now we've got the height and base of one rectangle, but we actually need to approximate the whole thing, right? So we need to get a number of rectangles, which is going to be very large, and we need to add all of those up. So we're going to get a sum of all of these areas of rectangles, and we're going to take a limit for the number of rectangles, the number of parts we're going to divide this interval up into. So the quite general integral from a to b of f of x dx is going to be the limit from n goes to infinity of our sum. So this sum is going to be the sum of all of these different rectangles of b minus a over n. So that's going to be each base. So that's going to be times f of a plus b minus a k over n. So basically what we've done here is we've constructed the kth area of a rectangle, and then we're going to sum all of the kth rectangles up, and we can take a limit to get an exact result for an integral. So maybe let's let n approach an even larger number, and we're going to see how close it actually gets. And this is only 50 parts, and we can let this go to infinity and we get the exact integral itself. So as we've just seen, this is just basically the horizontal part, and this part is the vertical part, which does vary. So let's see how we can use this result to solve our limit. So obviously we can choose any variables, it just needs to fit our sum. So maybe we can choose b equal to 1, so we're going to get b equal to 1 and a equal to 0. So that's actually going to give us this nice first part, which is the limit as n goes to infinity of 1 over n. So that's just b minus a, which is going to be 1, and then the sum from k equals 0 up to n of the function, and then a is equal to 0, so we're actually just going to get k over n. And at this point we can get this really nice insight on what's going on. So basically if we compare these two sums, here and here, there's only one difference. We've got this 1 over n, that's all the same, and then we've got this 1 over k over n squared plus 1, so this part over here. But actually, you can see the similarities pretty clearly, and we can just define a function f of x, which is going to be, so f of x is going to be 1 over x squared plus 1. So see if you understand why we've done that. It's exactly the correct function to get our sum we want. But that means that if we look at this integral over here, that we can actually write the integral from 0 to 1 of 1 over x squared plus 1 dx. And actually this is a pretty easy integral. So this antiderivative here is actually just standard. That's going to be the arctan of x evaluated from 0 to 1. And arctan of x evaluated at 0 is just 0, and at 1 is going to be pi over 4. So subtracting those from each other, we get pi over 4. And indeed, we can write our limit is equal to the integral from 0 to 1 of 1 over x squared plus 1 dx using the limit definition of an integral. So we've just basically reversed that kind of calculation, and now we've ended up with the nice result of pi over 4. So I'll maybe rewrite our first problem, which is going to be the limit as n goes to infinity of the sum from k equals 0 up to n of n over k squared plus n squared is equal to pi over 4. So really nice result using a nice technique, which is kind of a must-know, although of course it's not necessarily obvious. But once you see these, I guess a tip for later as well, once you see these combinations of limits, which are kind of tough, combining these variables for the sum, you can often use some nice Riemann sums to fix this and bring it into an integral problem. Sometimes easy, like this one, sometimes tough integral as well. But thank you so much for watching. I hope you enjoyed this interesting solve.